All right. Done with work for today. Made about 140, 150 bucks, I think. So I got a $20 tip in the very first order. That was pretty sweet. They don't get that very often, but it's the second time someone's asked me to bring something as soon as possible and then offering me that tip. So that was pretty sweet. So I did Bible AV 25 earlier. So I'm almost done with the book of Judges. So basically, what I've gotten from the Bible so far is mostly what not to do. Because the issue that I've had when I was arguing against the Bible before I started reading it, was that I believed that the Bible represented what the people are supposed to be like. But upon reading it, I realized that what God is and what He does is not making our lives comfortable and just doing things for us. But it's sort of like a symbiotic relationship. Whereas where the pursuit of God leads to certain benefits and certain just it's just I don't know, I can't even think of any downsides to the pursuit itself. Besides maybe just not the uncertainty behind it. Because it does feel uncertain because I did spend my whole life, being against it. But because basically all I've read so far is that the Israelites are just going to keep making mistakes over and over and over again. And so they're the chosen ones because that's who that's who what the Bible is talking about. That's who the Bible is chosen to focus on. It doesn't mean they're going to, well, at least so far from what I'm reading, it doesn't sound like they are going to get everything that they want. That the Israelites are no longer just based on the geographical region where they're from, even though we have a country named Israel. That really what it is that any of us can become God's chosen people individually by making individual choices to do that. And that it's only a choice. It can't be something that's forced. And so seeing all these like attempts at laws and stuff just doesn't make sense to me because you can't make someone believe in something that they read. Like that's just not how reality works. Easiest way to show someone how something works is to just demonstrate it. Yeah, that's the one thing I hate about school is that there was not as much demonstration as there could have been. There's not enough as much hands-on stuff as there could have been. So, anyhow, that's part of the reason why I'm doing this, and I realized that I could use my new niece that I haven't met yet. I'm meeting her tomorrow. My brother had a baby recently, and what I could do is I could create this system of learning for when she is old enough to think for herself or start asking those kinds of questions. And then you can just go to this, and this is where I'm just going to explain everything. So this is just this. I'm simplifying things just by just taking notes on the book so far, but really I'll be able to teach all of this stuff once I've gotten through the milestones, which I should probably talk about. So I'm still trying to figure that out, but actually I could go ahead and do that right now. Let's pop into here. Oh, no, not there. Sorry. Here. So, oh, that's right. I forgot I was working on that. Um, excuse me. So, milestones. So, basically, one, reading silently. Two, reading verbally. It's an R in there somewhere. 3, reading with 2 hands. 4, reading with 1 hand. So this is going to be typing, sign language. So it's 2 types there. And then with 1 hand, it'll be writing, drawing, yeah, I think that's really it. And then the goal after that, so that's basically I've by that time I'll have read it several times. And then what I want to be able to do is 5 scroll making, and that's going to include summarizing, keywords, and figures, images. So I'm talking like graphs, and just like little scale models, 2D representations, cross sections, all sorts of stuff. And then eventually 6 animations. So video, audio, maybe AI as well for a little automation, so on. But really, that's what I want to do. So if I can make this work right, I just found out today that Instacart, when I get a list of orders that I could choose from, I don't necessarily have to go to the specific store that's listed. So if I get a Kroger store like Fred Meyer, if I get that, but it's like in Salmon Creek, or if it's on Columbia House Boulevard, but I see that it's actually closer to the store that I'm closer to. So the store that I'm at is 117th. That's the one that I'll probably make my base of operations. I'll spend most of my time there. Um, Now, what I can do is if I see an order that's at a different store, I can actually shop at the 117th location. So if I notice that the deliveries are actually not too far off, and I don't have to drive too much further, maybe like an extra couple miles, then if it's a good order, it's a good order, and I could just shop for it at the 117th location. So I think that's a good thing. And then I also thought about something that I could do because I've been wanting to get a GoPro, but it was like, what can I do with that? And well, I was actually thinking of getting some rollerblades. So I used to love those, and that's uh, one big theme in my life right now is full circle thinking, and it would be great to actually become proficient at something that I loved as a kid, but never really stuck with because for some reason I used to think you would be gay for having it, but that's obviously not how being gay works. So, but I saw some videos on YouTube of people riding the streets at night in New York. And I was like, oh, it'd be really fun to just ride the streets of Vancouver, um, maybe do a little exploring while on foot. So, and then I could use that instead of getting a bike. I can use those as my method of travel to try to like go to the stores and stuff. So I think that'll really help build some of my nerves back in my feet because that's a complex motion. I think that'd be pretty fun. So, um, fruit boots, smiley face, get, smiley face, smiley face, smiley face, upside down smiley face. All right, yeah. So that's something I want, and then also um, projector or and those smart glasses, because those things would be sweet and I'd be able to do a lot of cool stuff with them. So, okay. So, reading silently will be what I do on my own time when I'm doing Instacarts and I don't feel like coming home. If I come home, I can go ahead and do a verbal reading. Um, and then once I've done those, just during my free time, I guess actually 1 and 3 I could do in my free time, where I could do typing or even handwriting. So, although the handwriting one, I'm actually thinking of getting this thing. It's a couple $100, um, but it's like a digital writing pad with screen. So it's basically like the writing pad that I'm using right now, but it has its own screen. I think that'd be really cool to have. I'll be able to do a lot of stuff with that. So those might be some Christmas presents that I get for myself. But I really need to get back into the typing and the. I should relearn sign language. That should actually be pretty easy because all I have to do is just figure out how to sign the words, and then come up with a program. Come up with a training program to demonstrate the habit of the signing. And then I want to start making scrolls. So I'll have to figure out where to buy the big rolls of butcher paper. But I think that's what I'm going to do it on. And then I was thinking of just doing, I'll do like a pencil outline or a pen outline, or even just like with markers. I haven't figured it out yet. I'd love to get into like watercolors or into like just regular painting. Just go buy a big bucket of paint and then just paint with it. I don't know. I'll figure it out eventually. But for right now, let's go ahead and hit the math. Openstax Algebra and Trig, section 1.3, radicals and rational exponents. Learning objectives. In this section, you will evaluate square roots, use the product rule to simplify square roots, use the quotient rule to simplify square roots, add and subtract square roots, rationalize denominators, use rational roots. A hardware store sells 16-foot ladders and 24-foot ladders. A window is located 12 feet above the ground. A ladder needs to be purchased that will reach the window from a point on the ground 5 feet from the building. To find out the length of the ladder, we can draw a right angle triangle as shown in figure 1 and use the Pythagorean theorem. Now we need to find out the length when squared is 169 to determine which ladder to choose. In other words, we need to find a square root in this section. We will investigate methods of finding solutions to problems such as this one. Evaluating square roots. When the square root of a number is squared, the result of this original number. So when the square root of a number is squared, the result is the original number. Since 4 squared equals 16, the square root of 16 is 4. The square root function is the inverse of the squaring function, just as the abstract is the inverse of addition. The subtraction is the inverse of addition. To undo squaring, we take the square root. In general terms, if a is a positive real number, then the square root of a is a number that, when multiplied by itself, gives a. The square root could be a positive or a negative because multiplying two negative numbers gives a positive number. The principal square root is the non-negative number that, when multiplied by itself, equals a. The square root obtained using a calculator is the principal square root. The principal square root of a is written as root a. The symbol is called a radical. The term under the symbol is called the radicand, and the entire expression is called a radical expression. So they have it right there. Yep. So this is the radicand. That's the radical. This is the radicand. And this is the radical. expression. So basically, radical plus radicand equals radical expression. So that's like the alchemical treatment of the idea. All right, so the definition of the principal square root. The principal square root of a is the non-negative number that when multiplied by itself equals a. It is written as a radical expression with a symbol called a radical over the term called the radicand. Example 1. Evaluate each expression. So evaluating square roots is the theme. That's 10 because 10 squared equals 100. So root 100 equals 10 squared rooted. Okay? And then root 16 is 4. Root 4 is 2. So one could say 2 squared equals 4. 4 squared equals 16. So root 16 equals 4. And, root 4 squared. And that equals root 4 squared. Oh, sorry, 2 squared. Something like that. I don't know. Square rooted, maybe? Question mark? Winky face? Sad? I don't know what that was. Actually, screw it. All right, using the product rule to simplify square roots. To simplify a square root, we rewrite it such that there are no perfect squares in the radicands. There are several properties of square roots that allow us to simplify complicated radical expressions. The first rule we look at is the product rule for simplifying square roots, which allows us to separate the square root of a product of two numbers into the product of two separate rational expressions. For instance, we can rewrite root 15 as root 3 times root 5. We can also use the product rule to express the product of multiple radical expressions as a single radical expression. So the definition of the product rule for simplifying square root is if a and b are non-negative, the square root of the product a times b is equal to the product of the square roots of a and b. So square root of ab equals the square root of a times the square root of b. Okay, example 2. Using the product rule to simplify square roots, simplify the radical expression. So root, dang it, keep hitting the button. 300 equals root 3 times root 100, but that is 10, so that equals 10 root 3. And then 162, a to the 5th, b to the 4th, square rooted. So 162, I'm going to go ahead and play around with that. That's going to be 2 times 81. Oh, there we go. Okay, so we have root 162 times root a to the 5th times root b to the 4th. Simplify root 2 times root 81 times. So I'm going to simplify this into a squared, a, b squared, b squared. All right? That becomes root 2 times 9 times a times root a times b. Combine everything. 9a squared b root 2a. Nice. All right, example 3. Using the product rule to simplify the product of using the product rule to simplify the product of multiple square roots. So root 12 times root 3. So that's the same as saying root 4 times root 3 times root 3. That's the same as saying 2 times root 3 squared equals 2 times 3 equals 6. 6. Sorry, I get myself excited sometimes. Here's my Scooby-Doo face. All right, using the quotient rule to simplify square roots, just as we can rewrite the square root of a product as a product of square roots, so too can we rewrite the square root of a quotient as a quotient of square roots. Using the quotient rule for simplifying square roots, it can be helpful to separate the numerator and the denominator of a fraction under a radical so that we can take their square roots separately. So we can rewrite the square root of 5 halves as the square root of 5 over the square root of 2. So the definition for the square root, the quotient for simplifying square roots, the square root of the quotient a divided by b is equal to the quotient of the square roots of a and b where b does not equal 0. So the square root of a divided by b equals the square root of a divided by the square root of b. Example 4. Using the quotient rule to simplify square roots. Simplify the radical expression. Square root of 5, 36. Well, that's the same as saying the square root of 5 divided by the square root of 36. The square root of 36 is 6. That equals 5 over 6. Sorry, square root of 5 over 6, yeah. So example 6. Using the quotient rule to simplify an expression with two square roots. So we have root 234 x 11th y divided by the square root of 26x to the 7th y. So all we have to do is separate the roots into their own simpler roots. So that's what I'm going to go ahead and do. So we have root 234 times root x to the 11th times root y divided by root 26 times root x to the 7th times root y. All right? So 234, let's divide that by 2. That'll be 117. Let's try this. 2, 1, 2, 0, 3, 1, 2, 1, 4, 7. Okay. That should be divisible by 3. So divide by 3. Goes into 11 3 times. That's 9. 27. 9. 39. Okay. So that's the same as saying root 2 times root 3. And then 39. That's another root 3. Times root 13 times root x squared. And that happens 5 times root x root y. Okay? Root 2, root 13. So that's 26. And then root x squared. There's 3 of those. Root x. Root y. Cancel like terms. Root 2's cancel. Those two are multiply. Those two cancel. Those cancel. So there's 2 left. Those cancel. Those cancel. Okay. So then what we get is root 3 times root 3. So that's root 3 squared times root x squared squared. Okay. And that's this here is x squared 9. Oh, sorry, 3 squared, so those cancel. So you get 3x squared. And that's the answer. That's one way. That's how you solve it. All right, adding and subtracting square roots. We can add or subtract radical expressions only when they have the same radicand and when they have the same radical type, such as square roots. For example, the sum of root 2 and 3 root 2 is 4 root 2. However, it is often possible to simplify radical expressions, and that may change the radicand. The radical expression root 18 can be written with a 2 in the radicand as 3 root 2. So root 2 plus root 18 equals root 2 plus 3 root 2 equals 4 root 2. All right, example 6. Adding square roots. Add 5 root 12 plus 2 root 3. Well, 5 root 12, that's the same as saying 5 root 4 root 3. But that's the same as saying 2. So it's 10 root 3 plus 2 root 3 equals 12 root 3. And there it is right there. Okay, subtracting square roots. Subtract 20 root 72a cubed b to the fourth c minus 14 8a cubed b to the fourth c. Okay, so I'm going to go ahead and do the I'm going to go ahead and pull as much out of the radical as I can, just to practice simplifying too. So 72 is, we know that's a multiple of 9. So that's the same as saying 20 times root 9 times root 8 times root a squared times root a times root b squared squared times c, root c, minus 14 root, I'll just say root 8 for now, times root a squared times root a times root b squared squared times root c. Well, that's the same as saying 3. This is the same as saying root 4 times root 2. That's the same as saying 2. So 3 times 2 is 6. So 20 times 6 is 120. That's the same as saying a. So a b squared root 2ac minus, that's a b squared root 4 and 2, that's 2. So minus 28 a b squared root 2ac. Now they have the same base. So 120 minus 28. And ab squared. So those are the same also. So these subtract. (120 minus 28 is going to be what? 92. ab squared root 2ac, question mark. Okay, cool. It has to be an absolute value, it looks like, just by convention. Cool. That's fun. I love stuff like this. All right, rationalizing denominators. When an expression involving square root radicals is written in simplest form, it will not contain a radical in the denominator. We can remove radicals from the denominators of fractions using a process called rationalizing the denominator. We know that multiplying by 1 does not change the value of an expression. We use this property of multiplication to change expressions that contain radicals in the denominator. To remove radicals from the denominator of fraction, multiply by the form of 1. That will eliminate the radical. For a denominator containing a single term, multiply by the radical in the denominator over itself. In other words, if the denominator is b root c, multiply by root c over root c. For a denominator containing the sum or difference of a rational and an irrational term, multiply the numerator and denominator by the conjugate of the denominator, which is found by changing the sign of the radical portion of the denominator. If the denominator is a plus b root c, then the conjugate is a minus b root c. Okay? Example 8, rationalizing a denominator containing a single term. Write 2 root 3 over 3 root 10 in simplest form. Okay, so that's just, we're just going to multiply both sides by root 10, or both top and bottom by root 10. So 2 root 3 over 3 root 10. We'll get rid of the root 10 by doing this. And that's going to equal 2 root 30 over, and that's going to be 3, so times, that squares it. So 3 times 10 is 30. 2 root 30 over 30. And then that's the same as saying root 30 over 15. Cool. There it is. Example 9. Rationalizing a denominator containing 2 terms. Okay, so let's go ahead and write it up here. 4 over 1 plus root. Sorry. Okay, try this again. 4 over 1 plus root 5. So, got to multiply by the conjugate. So, that's multiply what minus root 5? 1 minus root 5. So, that's going to be 4 minus 4 root 5 over, and then 1 plus root 5 minus root 5 minus 5. Actually, I'll do the whole thing. Minus root 5 so I'll just do plus. I'm sorry. Dang it. Plus root 5 times negative root 5. So that's going to be 4 minus 4 root 5 over 1. Those cancel. Minus 5 equals 4 minus 4 root 5 over negative 4. And then that's just going to be root 5 minus 1 over 1. Or just root 5 minus 1. Yep, there it is right there. Using rational roots. Although square roots are the most common rational roots, we can also find cube roots, fourth roots, fifth roots, and more. Just as the square root function is the inverse of the squaring function, these roots are the inverse of their respective power functions. These functions can be useful when we need to determine the number that, when raised to a certain power, gives a certain number. Understanding nth roots. Suppose we know that a cubed equals 8. We want to find what the number raised to the third power is equal to 8. Since 2 cubed equals 8, we see that 2 is the cube root of 8. The nth root of a is a number that, when raised to the nth power, gives a. For example, negative 3 is the fifth root of negative 243 because negative 3 to the fifth is negative 243. If a is a real number with at least one nth root, then the principal nth root of a is the number with the largest or the same sign as a when raised to the nth power equals a. The principal nth root of a is written as root n a, where n is a positive integer greater than or equal to 2, and the radical expression n is called the index of the radical. So, the definition of the principal nth root: if a is a real number with at least one nth root, then the principal nth root of a is written as the nth root of a is a number with the same sign as a when raised to the nth power equals a. The index of the radical is n. Example 10. Simplify each of the following. 5, or the fifth root of negative 32. So that's going to be negative 2. Because negative 2 to the fifth power, so because it's an odd power, will stay negative. Because you do it 5 times. 2 is 4, 8, 16, 32. All right? Fourth root of 4 times the fourth root of 1024. So 1024 divided by 2 is going to equal 517. Sorry, that's not right. 512 divided by 2. That's going to be 206. And then again, 206 divided by 2 equals 103. Okay. So that's 1, 2, 3, 4. So we're going to have the fourth root of 2 times the fourth root of 2. But so that's actually I'll do this. 2 squared times the fourth root of 2 cubed times the fourth root of 103. So then what we'll do is we'll have the fourth root of 2 times 2, because I have 4, 1, 2, 3, 4, 5, so 4 of them. Times root 103 times, that's it, right? Oh, I guess the whole thing can go together. Never mind. I should have just multiplied them first to see. Okay. This one's going to be negative 2x squared over 5. Yeah, there it is right there. But I just did mental math on that one. So 8 cubed is, or 2 cubed is 8. So a 2 can get pulled out of there. Because when a 2 is applied to it, it makes 8 on the inside. All right, and then x to the 6th, that's cubed twice. So I can pull out an x squared. And then 125 is the cube root of 5. Sorry, 125 cube rooted is 5. Guess I'll multiply those probably. But yeah, anywho. All right, using rational exponents. Radical expressions can also be written without using the radical symbol. We can use rational fractional exponents. The index must be a positive integer. If the index is even, then a can be negative. A to the 1 over n power equals the nth root of a. We can also have rational exponents with numerators other than 1. In these cases, the exponents must be a fraction in lowest terms. We raise the base to a power and take the nth root. The numerator tells us the power and the denominator that tells us the root. So a to the m over n equals the nth root of a to the mth power, which equals the nth root of a to the m. All the properties of exponents that we learned for integer exponents also hold for rational exponents. So the definition of rational exponents. Rational exponents are another way to express principal nth roots. The general form for converting between a radical expression with a radical symbol and one with a radical exponent is a to the m over n power equals the nth root of a all to the mth power, which is the same as a to the m nth root. Okay, example 11. Rewriting fractional exponents as radicals. Write 243 to the 2/3 as a radical. Simplify. Sorry, 343 to the 2/3. So 343 to the 2/3 is a radical. So that's going to be the cube root of 343 squared. Well, 343, I can divide that, I'm guessing, by 3. No, maybe not. Let's see. 343, 3, 1, 3, 0, 4, 1, 3, 1, 3. Nope. Let's try 343, 7. Goes into there 28 times 4. 28, 2, 1, 6, 3. Goes into 63. 7 times 7, 7 times 8, 56. 7 times 9 is 63. 49. That is also 7 times 7. So that's the same as saying 7 cubed. So 343 equals 7 cubed. So equals root 3, 7 cubed squared. So that's going to be 7 squared equals 49. There it is. Okay. Example 12, writing radicals as rational exponents. Write 4 over the 7th root of a squared using a rational exponent. So 4 over 7 root a squared equals 4 a squared to the 1/7. Oh, I see. Okay. So that's going to see 4 over, sorry, it's been a while since I've done something like this. So that's going to be a to the 2/7. But if I want a to go up into the numerator like they have it, so if that's, I guess that's the standard form, is to get the radicals out of the exponent. Makes sense. So that's going to be multiplied by a to the conjugate, 7 over 2. So, oh, sorry, hold on. No, that doesn't work. I have to use the rule of addition. So 4 over a to the 2/7 times a to the negative 2/7 over a to the negative 2/7. So that's the same as saying 4a to the negative 2 over 7 over a to the 2/7 minus 2/7 power. But that is 0. A to the 0 is 1. So that equals 4a to the negative 2/7, which is there. Oops. Okay. Example 13, simplify using rational exponents. Okay. Let's just go ahead and multiply everything through. So that's 5 times 2 times 3 times x to the 3/4 times x to the 1/5. So that's the same as saying 10/30 x to the 3/4 to the 1 minus 1/5. Common denominator is 20. So that's the same as saying 30 x times 5, 15 over 20, minus times 4, 4 over 20. That's 11 over 20. So equals 30x to the 11 over 20th power. Oh, is it plus? I minused, dang it. I meant plus. Okay, well, plussing it, 15 plus 11. Oh, sorry, it's not 11, 4. 15 plus 4 is 19. That's a plus. That's a 19. 19. Yep, that's what they got. So then 16 over 9 to the negative 1 over 2 equals 16 to the negative 1/2 over 9 to the negative 1/2. That equals 9 to the half over 16 to the half equals root 9 over root 16 equals 3/4. There it is. All right. And that is it. So 10, 7, 20, 34. Just when I remember to write date and time down. All right, so that's the end of 1.3. Oops.